In physics, when two independent teams measure the same thing and get different results, there are three possibilities. The first team made an error. The second team made an error. Or something in our understanding of the world is fundamentally wrong. The Hubble tension has eliminated the first and second possibilities, at least the third. Here is the problem in its simplest form. We have two ways to measure how fast the universe is expanding. Two entirely independent methods developed by different teams with different instruments across decades of rigorous work. These two methods give answers that do not agree. One says the universe is expanding at about 67 kilometers per second per megaparsec. The other says 73. The difference is 9. And this difference is real, statistically confirmed at a level physicists normally reserve for major discoveries, 5 sigma, meaning a probability of less than 1 in 3.5 million that it is a random error. This is not an instrumental imprecision. It is not a calculation error. It is not an undetected selection bias in the data. Every hypothesis of that kind has been examined, tested, and ruled out over the years. In January 2500, a meeting of the American Astronomical Society, some astrophysicists stopped calling it a tension. They started calling it a crisis. The Hubble tension did not emerge overnight. It developed gradually, keeping pace with improvements in instrumentation, like a crack in a wall you believe solid that widens imperceptibly year after year until the moment you can no longer ignore it. In the 2000s, the discrepancy between the two methods sat at around 2 sigma statistically present, but in the gray zone where researchers can still invoke unidentified systematic errors and hold on to hope. Sigma, in physics, is a hint, not a proof. In 2013, the Planck satellite results sharpened the CMB measurement to the point where the value of 67 was unassailable on the early universe side. In 2016, the Ishiui's collaboration published its most precise local results at the time, 73.2 AU. The gap was at 3 sigma, a serious anomaly. In 2019, after further refinements, the tension reached 4 sigma. At that point, speaking of a statistical fluctuation was no longer reasonable. Both methods had been scrutinized thoroughly. New independent analyses, using standard candles other than Cepheids, notably the tip of the red giant branch, had confirmed values close to 73. New CMB analyses confirmed values close to 67. Then James Webb launched, and measuring with it, the hope that the error would come from the local measurements permanently faded. What makes this situation particularly uncomfortable is that James Webb, the most precise instrument ever built to observe the universe, made the problem worse. James Webb was supposed to resolve the tension. It had the resolution to verify local measurements with unprecedented precision. It did so, and the answer it got is not 67. It is still around 73. If both methods give different results, and both methods are correct, then our model of what happens between the beginning of the universe and today is wrong. Not slightly imprecise. Wrong in a way that implies something important is missing from our understanding of the cosmos. That something has no name yet. Physicists have hypotheses. They have candidate models, but none commands consensus, none fully solves the problem, and several imply radical modifications to theories we have taken for granted for decades. Before understanding what this implies, you need to understand what is being measured. Not the term, the physical reality behind the number, because the Hubble constant is not an abstract figure in an equation. It is a measurement of the entire history of the universe, encoded in the light we receive from galaxies billions of light years away. And understanding why two independent methods arrive at different answers first requires understanding what each of those methods actually measures. The Hubble constant, what it actually measures. In 1929, Edwin Hubble made an observation that changed cosmology forever. Measuring the light of distant galaxies, he found that almost all of them were moving away from us, and that the farther a galaxy was, the faster it was receding. The relationship was linear. Double the distance, double the recession speed. It was the first direct evidence that the universe was not static. It is expanding. That discovery had something improbable about it, even from the start. Hubble was not directly observing an expansion. He was observing a redshift, the fact that light from distant galaxies is stretched toward longer, redder wavelengths, the way the sound of a receding ambulance drops in pitch. That shift is the signature of the speed at which a light source is moving away from the observer. By measuring this shift for dozens of galaxies and comparing it to estimated distances, Hubble found the relationship that bears his name. What we today call the Hubble constant is the slope of that relationship. And measuring that slope with precision, knowing exactly how fast a galaxy recedes for each megaparsec of distance, became one of the central quests of modern cosmology. The Hubble constant, written h/0 h0, measures the current rate of that expansion. More precisely, it expresses how many kilometers per second a typical galaxy recedes from us for each megaparsec of distance. 1 megaparsec is about 3.26 million light-years. What that means concretely, a galaxy 1 megaparsec away is receding at about 70 kilometers. A galaxy 10 megaparsecs away is receding at about 700 kilometers. A galaxy 1,000 megaparsecs away is receding at 70,000 kilometers, about 23 of the speed of light. and a galaxy at around 14,000 megaparsecs is receding so fast that its light can no longer reach us. That is the edge of the observable universe. But h-now does not just measure the current speed, it encodes the complete history of the expansion. A universe that expanded faster in the past has a different h-0 than one that expanded more slowly. A universe with more dark matter or dark energy has a different h-0. HDAE is, in a sense, the fingerprint of the entire cosmic dynamic. That is why the difference between 67 and 73 is not trivial. A 9 difference in HH test row is not a precision gap. It is a gap implying that the universe has a different expansion history from what one of the two models predicts. And since both models are built on different physics, one on what we observe today, the other on what we observe in the oldest light in the universe, the question is, which of these two physics frameworks is wrong? The value of h-ow also determines the age of the universe. A higher h0 means the universe expanded faster, so it is younger than we thought. A lower h-no implies slower expansion, an older universe. With h over 67, the calculated age of the universe is about 13.8 billion years. With h-now 73, it would be roughly 12.5 billion years. That difference of about 1.3 billion years has consequences. Some of the oldest stars observed in globular clusters have estimated ages of close to 13 to 14 billion years. In a universe with HAO 73, those stars would appear nearly as old as the universe itself, or older by some estimates, which is physically impossible. The Hubble tension is therefore not just a question of expansion speed. It touches the temporal coherence of the entire cosmic story. Understanding both methods in detail is what allows you to measure the gulf between them. The first method, the echo of the Big Bang. To understand the first method, you have to travel back very far back. Not to the Big Bang itself, which is by definition inaccessible to direct observation, but to 80,000 years after it. At that precise moment in cosmic history, something important happened. Until then, the universe had been an opaque plasma soup, electrons, protons, photons all mixed together in a state so hot and dense that light could not travel freely. It was constantly absorbed and re-emitted, unable to escape. The universe was blind to the light it contained. At 38,000 years, the temperature had fallen far enough to about 3,000 degrees for electrons and protons to combine into neutral hydrogen atoms. And in that instant, the universe became transparent. Light, freed for the first time, exploded in all directions. That flash of liberation is still present today. It has simply been stretched so much by the expansion of the universe over the 13.8 billion years that followed that it became a faint diffuse microwave radiation at a temperature of 2.7 degrees above absolute zero. This is called the cosmic microwave background, or CMB. The ESA's Planck satellite, which observed the CMB from 2009 to 2013, mapped this radiation with extraordinary precision. The tiny temperature fluctuations in the EMB variations on the order of 100,000th of a degree correspond to density variations in the primordial universe, the seeds of everything that exists today. Galaxies, galaxy clusters, cosmic filaments, all of it was there, in embryonic form, in those ripples of the KM. These fluctuations have a characteristic structure. In the primordial plasma, before the liberation, acoustic waves propagated exactly the way sound waves propagate through air, but at a cosmic scale and at a considerable speed. These waves had a preferred wavelength, determined by the speed of sound in that plasma and by the age of the universe at the moment of liberation. That characteristic wavelength, called the sound horizon, is a physical ruler encoded in the CMB. Its physical size can be calculated precisely from well-understood nuclear and atomic physics. Its apparent angular size in the sky can be measured directly in the CMB. To put this in perspective, imagine holding a 1-meter ruler at arm's length. By measuring the angle it subtends in your field of vision, and knowing its physical length, you can calculate the distance at which you are holding it. That is exactly what cosmologists do with the CMB sound horizon, except the ruler is about 450 million light-years long, and they are measuring it at 13.8 billion light-years away. Planck's precision on this measurement is such that the sound horizon's angle is known to better than 0.1. By comparing the known physical size of this ruler to its observed apparent size, you get the distance to the CMB. Combining that distance with the equations governing the universe's expansion under the standard model, the LEC-DM model, lambda CDM, integrating ordinary matter, and dark energy yields a predicted value for H0. Planck's answer: 67,270.60 km per megaparsec, with a precision of less than 1, one of the most precise measurements in modern astrophysics. And in 2055, the Atacama Cosmology Telescope ACT performed its own CME measurements, independently of Planck, with different technology, in a different observatory, on a different continent. That independence matters. ACT and Planck do not use the same detectors, the same observation frequencies, or the same analysis algorithms. Their scientific teams are separate. If both gave the same answer because of a shared bias, that bias would be extraordinarily difficult to imagine. ACT's answer? Approximately 67. The same? 2 independent instruments, 2 separate teams, 1 answer. The universe is expanding at 67 kilometers per megaparsec. The second method? The cosmic distance ladder. The second method starts from the other end, not the primordial universe. The universe of today, measured directly, with instruments observing real stars in real galaxies at real distances. The principle is called the cosmic distance ladder. It is a multi-rung construction, each rung building on the previous one, extending the measurement of distances ever farther into the universe. First rung, parallax. For the nearest stars, distance can be measured directly by triangulation the same way a surveyor measures the distance to a tree by observing its angle from 2 different positions. Earth orbits the Sun. By observing a nearby star from 2 opposite positions in Earth's orbit, separated by 6 months, the star appears slightly shifted relative to the very distant background stars. That shift, the parallax, is directly linked to the distance. ESA's Gaia satellite has measured precise parallaxes for more than 1 billion stars in the Milky Way. This is a direct geometric distance with no physical assumptions. It is exact. Second rung, Cepheid variable stars. These are stars whose luminosity varies periodically. They pulse, expanding and contracting over periods of a few days to a few weeks. Their remarkable property, discovered by Henrietta Swan-Leavitt in 1912, is that the pulsation period is directly linked to intrinsic luminosity. A Cepheid that pulses over 10 days is exactly as luminous as another Cepheid pulsing over 10 days, regardless of which galaxy it is in. This is what is called a standard candle, an object of known luminosity, allowing distance to be calculated from its apparent brightness in the sky. The fainter a calibrated Cepheid appears, the farther away it is. By calibrating Cepheids with Gaia parallaxes, then identifying Cepheids in increasingly distant galaxies, astronomers extend the measurement to tens of millions of light-years. Third rung, Type Ia supernovae. When a white dwarf, the dense remnant of a dead star, accretes enough material from a neighboring star to exceed a precise critical mass, the Chandrasekhar mass, about 1.4 times the mass of the Sun, it explodes in a thermonuclear supernova. That explosion always has approximately the same intrinsic luminosity, a standard candle far brighter than Cepheids, visible across billions of light-years. By calibrating these supernovae using galaxies where Cepheids have been identified, then measuring their apparent brightness in even more distant galaxies, the ladder is extended to most of the observable universe. Comparing the calculated distance with the recession velocity of those distant galaxies gives H0. At the Shishu's collaboration Supernova Chio4, the equation of state refined this measurement over years, adding galaxies, tightening calibrations, testing every rung of the ladder for potential biases. The result was verified by other teams using additional methods. Time delay gravitational lensing, baryon acoustic oscillations in the galaxy distribution, galactic megamasers, intense microwave radiation sources in distant galaxies whose distance can be measured geometrically. All of these independent local methods converge in the range of 7,074 kilometers per megaparsec. None reaches down to 67. Shinui's final answer, 73.213 kilometers per megaparsec. 2 independent methods, 67 versus 73. 9% gap, 5 sigma of statistical significance, the same threshold used to announce the discovery of the Higgs boson in 2012. James Webb in between. And what it found, the natural reaction, when 2 methods give different results, is to look for the error. In the Hubble tension case, the most obvious suspect was the second rung of the ladder, the Cepheids. These stars sit in dense galaxies where stellar fields are crowded. Was the Hubble Space Telescope old, lower in resolution, blending the light of multiple stars into a single point, distorting the measurement? That is exactly the question James Webb could answer. With angular resolution superior to Hubble's in the infrared, capable of resolving individual stars in crowded environments where Hubble saw blurry blobs, James Webb was the ideal tool for checking Cepheid measurements. In 2023, the first James Webb analyses of Cepheids and supernova host galaxies were published. The answer was unambiguous. Hubble's Cepheid measurements were correct. Crowding contamination from neighboring stars was not sufficient to explain the discrepancy. The local value stayed around 73. In 2044, Webb and Hubble published a joint result confirming that conclusion. It was a pivotal moment. There had always been a community of researchers who held out hope that the error would come from the local measurements that Hubble, old and limited in resolution, had simply mismeasured the Cepheids in crowded fields. That exit door is now closed. James Webb closed it with the precision that is its signature. And in 2025, additional measurements using an alternative method, the tip of the red giant branch, or TrueGB, another standard candle independent of Cepheids, returned values between 70 and 72 kilometers per megaparsec. These results are slightly lower than 73, fueling an active debate about the relative precision of different local methods. But even at 70 or 71, the value does not reach 67. The gap persists stubbornly at 5 sigma. But James Webb did something else in parallel, something nobody had originally asked of it, which added an entirely new dimension to the problem. Looking deep into the primordial universe, the first few 100 million years after the Big Bang, James Webb found galaxies that should not have been there. Massive, luminous, mature galaxies existing barely 300 to 500 million years after the Big Bang, at a moment when the standard model predicts the universe was still too young to have formed such structures. These galaxies have 10 times, sometimes 100 times more stars than the LTM model simulations predict for that era. To understand how problematic this is, you need to understand how galaxies form in the standard model. According to LIST-EMA, structure forms hierarchically. First, small clumps of dark matter aggregate under gravity. Then gas accumulates within them, forms stars, and progressively merges into larger structures. This process takes a lot of time. Forming a massive galaxy takes several hundred million, sometimes several billion years. Finding such galaxies at 300 or 500 million years after the Big Bang is like finding a century-old oak tree in a forest planted last year. The timeline does not work. Some researchers argue that these impossible galaxies, the term appeared in the scientific literature itself, could be linked to the Hubble tension. If the primordial universe expanded faster than LIST-EMA predicts, it would have had effectively more time to form structures. The local matter density would have been different. Galaxy seeds would have developed more quickly. A universe expanding at HHO 73 in its early phases would have a slightly different structural formation history from a universe at HHO 67, and that difference could explain the early massive galaxies. This is not directly the Hubble tension. It is a different tension sometimes called the massive galaxies tension, but both may share the same root. If the universe expanded faster in its youth than LIST-EMA predicts, it would have had more effective time to build massive structures. Both tensions HNO and the impossible galaxies could be pointing toward the same gap in our physics. James Webb, built to answer questions, has multiplied the questions. That is not a failure of the instrument. It is exactly what the best instruments in the history of science do. They reveal the limits of the model used to interpret them. Galileo did not build his telescope to refute Aristotle, but what he saw through the eyepiece made the Aristotelian model untenable. James Webb was not launched to refute LIST-EMA, but what it sees, from both ends of the universe's timeline, makes it increasingly difficult to maintain LIST-EMA without modification. What this breaks in our physics, the standard model of cosmology is called LIST-EMA lambda, CDM. The lambda represents dark energy, the mysterious force accelerating the universe's expansion. CDM stands for cold dark matter, the invisible matter that makes up about 27% of the universe's energy content, that does not radiate and does not interact with light, but whose gravity holds galaxies and galaxy clusters together. This model, developed progressively since the 1980s and refined by decades of observations, is one of the most remarkable achievements of modern physics. It predicts with extraordinary precision the large-scale structure of the universe, the way galaxies organize into filaments, sheets, and voids. It predicts the composition of the CMB. It predicts the abundance of light elements formed in the first few minutes after the Big Bang. It predicts the age of the universe, 13.8 billion years. For dozens of different predictions, LTM give the right answer, except for H-EVA. The problem is that LIST-EMA is built in such a way that H0 is not a free parameter you can simply adjust. It is constrained by all the other parameters simultaneously: the density of ordinary matter, the density of dark matter, the amount of dark energy, the curvature of the universe. To force Hausnaua to rise from 67 to 73 in this model, something else has to change, and that something else immediately conflicts with other observations that independently constrain those parameters. This is the Gordian knot of the Hubble tension. Every simple solution creates a new problem. Try to raise H0 in the model by increasing the amount of dark energy, and you break the predictions on large-scale structure formation. Change the dark matter density, and you break the CM predictions. Modify the curvature of the universe, and you conflict with Planck data constraining that curvature to virtually zero. The model is so finely tuned to so many observations that there is no simple lever to pull, which implies one of two things. Either something in the physics of the early universe, something between the Big Bang and the CME in the first 380,000 years, is different from what the standard model assumes. Or something in the local physics, in the way we measure distances with Cepheids and supernovae, introduces a systematic bias that James Webb has not yet found. James Webb has firmly reinforced the second hypothesis: local bias is not sufficient to explain the gap. That leaves the first: something in the physics of the primordial universe is wrong. That is not a conclusion drawn lightly. SDM is the result of decades of work by thousands of physicists, verified by hundreds of independent observations. Saying something in it is wrong means saying that the most carefully constructed edifice in modern cosmology has a structural flaw, not a cosmetic crack, a flaw in the load-bearing structure. The question is, which part? The hypotheses and the unknown. Since the Hubble tension reached the 5 sigma threshold, the cosmological community has generated dozens of alternative models. Most are variations on a few main themes. The most widely discussed is called early dark energy, or EDE. Idea goes like this. In the standard model, dark energy, the lambda in LIST-EMA, is a cosmological constant. It has always existed at the same density, unchanging. But what if there were an additional form of dark energy, active only in the period just before the CM was released, that subsequently dissipated? This early dark energy would have accelerated the universe's expansion just before the CM was emitted. That would have reduced the physical size of the sound horizon, the ruler encoded in the CMB. And with a smaller ruler, the same angular CMB measurement would imply a shorter distance, which would require a higher HENO to remain consistent. The predicted value rises. The problem shrinks. On paper, AD works partially, but it introduces its own tensions. It slightly modifies the large-scale structure distribution of the universe in a way that conflicts with other observations of galaxy distribution. It is not a clean fix. A second hypothesis comes from recent data from DESI, the Dark Energy Spectroscopic Instrument, a ground-based instrument in Arizona, mapping the distribution of millions of galaxies to measure how dark energy influences the expansion. DESI's 2004 data suggested something unexpected. Dark energy may not be constant. It could vary over time, perhaps stronger in the universe's more recent past than today, or the reverse. If dark energy evolves, the LESIDM model built on a fixed cosmological constant is incomplete. A dynamic dark energy could potentially reconcile the two HNO measurements, though DESI's data are not yet sufficient to confirm this variation definitively. A third line of inquiry, the local void model. We may live in a region of space slightly less dense than average, a kind of local cosmic void. In an underdense region, matter tends to flow outward toward surrounding denser regions. This local matter flow could add an extra contribution to the recession velocity of nearby galaxies, artificially inflating our local HEOS-ROM measurement. Problem? Studies of local matter density suggest this void, if it exists, is not deep enough or extended enough to explain a 9 gap. There are also more exotic proposals. Additional relativistic particle species in the primordial universe, not predicted by the standard model of particle physics, perhaps sterile neutrinos, perhaps a new type of lightweight particle that would have altered the expansion speed before the CME was released. These extra particles, if they exist, would have contributed to the energy budget of the primordial universe, modifying expansion dynamics in a way that raises HERO without deforming the CMB detectably with current instruments. Modifications to Einstein's gravity at cosmological scales represent another avenue. Perhaps general relativity, precise as it is at the scale of the solar system and stars, needs modification to describe gravity across billions of light years. Interactions between dark matter and dark energy completely decoupled from each other in the standard model could also subtly alter the universe's expansion history. What all these hypotheses share is that they all postulate the existence of something we have not yet directly observed. An additional component, an additional process, additional physics. The Hubble tension draws the outline of a hole in our knowledge, a space in the theory that something must occupy, which we have not yet identified. None of these hypotheses is confirmed. All have problems, and that is precisely where the value of this crisis lies for physics. It delimits the space where something new must exist. The Hubble tension will be resolved in one of two ways. Either an as-yet unidentified systematic bias in one of the two methods will be found, which seems increasingly unlikely as measurements become more refined. Or new physics, a component or process absent from the current LEDM model, will be confirmed by future observations. The second scenario is the most scientifically exciting and the most conceptually unsettling. Because a modification of LESIDM is not a minor correction to an otherwise correct model. LESIDM is the complete architecture of our understanding of the universe from the Big Bang to today. It integrates Einstein's general relativity, the particle physics of the standard model, Hubble's observational cosmology, Planck data, large-scale structure. Everything is connected in this model. Finding that a central prediction is wrong at 5 sigma means finding that the edifice has a structural flaw, not a cosmetic one. What James Webb has done by confirming that the local measurement is correct and that the gap does not disappear with greater precision is close the most convenient exit. Instrumental error is not the answer. And by finding impossible galaxies in the primordial universe, James Webb has simultaneously opened another window. Perhaps the flaw in the model is visible from more than one angle. Cosmologists are now in a position that is uncomfortable but fascinating. They know something is wrong and they do not yet know what. These are the conditions in which great discoveries are made. Not when everything fits, but when something resists. There is a strange symmetry worth noting. Dark energy itself, the lambda of LESIDM, was discovered in 1998 precisely because supernova measurements gave an unexpected answer. The expansion of the universe is accelerating rather than slowing. That discovery, which surprised everyone, earned its authors the Nobel Prize in 2011. It forced the introduction of a new component into the cosmological model. The Hubble tension could be the next chapter of the same process. A measurement that resists, that does not disappear when you look harder, and that ultimately forces a revision of the edifice. The difference between 67 and 73.9%, 5 sigma, is not an abstract number in a scientific paper. It may be the trace of a physics that exists and that we have not yet found. A component of the universe, a process, an interaction, something that was there from the beginning, that shaped the entire expansion history, and that our models have not yet been able to describe. There is a question physicists have been asking in private for several years, and increasingly in public. Is the Hubble tension a sign that we are approaching a scientific revolution comparable to quantum mechanics at the start of the 20th century or general relativity in 1915? Those revolutions happened in similar contexts, precise measurements yielding results inexplicable within the existing framework, anomalies the best minds of the era could not eliminate through instrumental corrections, theories that ultimately forced a rethinking of fundamental assumptions about the nature of space, time, and matter. The honest answer is that nobody knows. The Hubble tension could, like a few famous anomalies in the history of physics, eventually resolve in a more subtle instrumental bias than anyone anticipated. It could also mark the beginning of a period of fundamental questioning in cosmology. What is certain is that the instruments arriving in the coming years, the Vera Rubin Observatory on the ground, ESA's Euclid Space Telescope, NASA's Roman Space Telescope, will map hundreds of millions of galaxies with unprecedented precision. They will measure H-NOAA through new independent methods. They will constrain early dark energy hypotheses with data we do not yet have. The answer is coming, but it is not here yet. And in the meantime, we are in the uncomfortable and fascinating position of knowing with certainty that something is wrong without knowing exactly what. We are measuring the universe from two opposite ends. We are walking toward each other, and we are not arriving at the same place. What lies between them and that 9% gap is what we are looking for. Introduction: there is an unwritten rule in physics. When two independent methods measure the same thing and get different answers, find the error. Check the instruments. Revisit the assumptions. Start over. The Hubble tension has followed that rule for 20 years. Two independent methods measure how fast the universe is expanding. One looks at the echo of the Big Bang, the oldest light in the universe, emitted 80,000 years after everything began. The other looks directly at stars and galaxies in the present universe and measures their recession speed. One gives 67 kilometers per megaparsec. The other gives 73. 9% difference, and nobody finds the error. James Webb was supposed to settle it. With resolution superior to anything built before it, it could verify local measurements with unprecedented precision. It did, and its answer is not 67. It is still around 73. There is no instrumental error. The gap is real. In January 25, some astrophysicists stopped calling it a tension. They started calling it a crisis. Because at 5 sigma, a probability of less than 1 in 3.5 million, that it is chance this is no longer a statistical artifact. It is a fundamental disagreement. And if both methods are correct, then something in our understanding of the universe is wrong. In this video, we are going to see what the Hubble constant actually measures and why a 9 difference is not a rounding error. It is a contradiction in fundamental physics. We are going to see how each of the two methods works and why each is defended by different teams with different instruments over decades. We are going to see what James Webb found looking at both ends of the universe and why its discoveries made the problem worse instead of better. We are going to see what this breaks in the standard model of cosmology. And we are going to see the hypotheses physicists have proposed to explain this gap and why none has yet convinced everyone. Stay through the final section. Because what the Hubble tension implies about what we do not yet understand about the universe is larger than the gap itself.